And be here. Little known fact, the last time I was in this spot, I was defending my PhD thesis many years ago. Yeah, so I actually was a PhD student here at Boyce Thompson Institute, and in fact, I just wanted to start out by giving a little bit of intro to my history. As Maria said, I was in her lab, and I absolutely adore avascular mycorrhizae, and to tell you the truth, switching away from that topic broke my heart a little bit. In fact, I've been debating getting a tattoo to commemorate it, but it may happen sooner than later. However, it wasn't, an easy ride for me, and I just want to start by saying this to a lot of you in this room who are deciding what to do with your futures, and you're probably aware by now there are lots of different options. Academia is a great one, and industry is a great one, and at some times you might feel like you're not cut out for the current position you're in. Well, little known to most of you in this room, it took me 9 years to finish my PhD. And I'm surprised Maria didn't kick me out formally before I finished. Thank you for letting me finish. It was really hard, and this is just a moment I wanted to say. I was struggling deeply with depression. And as you can see, it's not the end to all. And I would just urge that everyone here in your journey through your careers, check yourself, check your mental health. Don't be afraid to talk to counselors, talk to friends, talk to mentors. Depression is real. Address it, and you can move past it and be the great person that you have the potential to be. So that's my story. After I finished, I will also give a shout out that I tried for 2 years. I was actually working in the BTI communications. I was writing press releases, working on the website, so that was another avenue that I explored before finishing my PhD and going back and doing my postdoc, which was a really, really cool position as well, and definitely look into it as general. As a scientist, it's really great to learn how to communicate what you do very well. So yes, then once I finished my PhD, I went to the Barstow lab in biological engineering, and a lot of this talk, I'm going to give an intro to rare earth elements so you know what the heck I'm talking about, because it's not about plants. And then a lot of it is going to talk about my postdoctoral research and what we were able to find that really drove us to found the company. And then I'm going to transition into a little bit more of what we've been doing at the company and what our business model is starting to look like, the traction with customers, to give you a sense of what it's like to take research and results from an academic lab and try to translate that into a commercial reality. All right, so to start, a little background on why we're doing this. So we all know that climate change is real, and avoiding carbon dioxide and greenhouse gas emissions is a huge prerogative in order for the planet to survive. And some of the most polluting industries, we could eliminate over half of their greenhouse gases today with current technologies using renewable energy. The problem is that in order to build enough renewable energy infrastructure, we are going to need far more rare earth elements and many other critical metals in order to meet the demands for that energy. So right off the bat, what am I talking about when I say rare earth elements? Specifically, I'm referring to the lanthanide series. So from lanthanum to lutetium, these are all rare earths. And then we lump scandium and yttrium in there as well. They all are very similar in their chemistry. They occur in the Earth's crust together. This is significant because they're very difficult to separate from each other. But they all have really unique properties that make their individual applications necessary. So we do need to separate them, and often in very high purity. They are essential for most of today's electronics. They're in high efficiency lighting, your mobile phones, your laptop computers, power drills. Basically, they're running the modern world. We absolutely need these metals. And just as an example, I love this demonstration. In just an iPhone, you can see all the different places that you might find rare earth elements. Both the vibrator and the speaker are using rare earth elements that are important for magnets. So neodymium and praseodymium, often lumped together as NdPr. This is important. I talk a lot about that in this presentation. Terbium and dysprosium are also magnetic, less important than neodymium and praseodymium, but those are the 4 big ones that we're going after when we talk about magnets. Also colors, europium, yttrium, terbium, these are all they convey interesting colors to your screen. They're in the fluorescent lights. And then also cerium, lanthanum, praseodymium, they can be used as fine glass polishers. So these uses really are abound throughout electronics in general. But most importantly, when we talk about combating climate change, I've already talked about this, they're super important for renewable energy infrastructure. They make up those strong, lightweight magnets that power the wind turbines and electric vehicle motors. To give you a sense, the permanent magnet crystal structure doesn't have that much neodymium, but if you take one part of that sintered metal to make the magnets, you've got huge amounts of magnets in the actual turbine, which then is just for one offshore wind turbine. So this adds up very quickly to power the wind turbine to give us renewable energy. So here's the thing. They're called rare earth elements, but they're not actually rare. In fact, neodymium alone is among the more abundant metals in the Earth's crust. The problem is they're just rarely found in concentrated deposits. They are locked up in chemical structures that are very difficult to leach and get apart. You have your copper, gold, they occur in ore strips. We can mine them. We also have methods for getting them out with chemicals as well. And so what this means is to get the rare earths, it requires a lot of energy and inputs to actually extract and refine them. So for that wind turbine, offshore wind turbine, it requires over 1 ton of rare earth elements, specifically NdPr, neodymium praseodymium. To get that ton actually results in exorbitant amounts of environmental hazardous waste. To mine, we get a lot of radioactive waste because there's often thorium and uranium in the minerals that we're mining these from. And also the separations require high amounts of solvents. But on average, you're looking at about 65 tons of CO2 equivalent per ton of rare earths that you're making. So if you think of renewable energy infrastructure as offsetting that, you have to think about the embedded material cost as well. So basically what this has led to, let's think about world dynamics, global dynamics, is that because of the environmental hazards over the past 2 decades, the world has kind of outsourced its production, and China has really picked up on producing the rare earth elements. So this brings us to the second huge problem, is that China is producing over 90% of the refined rare earth elements that the world uses today. And this is huge. This is a giant supply chain risk. The government controls it. They can moderate the prices. But also when tensions are high, as they tend to be, especially with the Taiwan crisis, we're looking at a potential supply chain and national security risk. We have defense electronics that utilize rare earths. And the US has actually specified you cannot use Chinese rare earths in defense applications, but at this point, hands are tied. We can't get it, except from China, basically. So at REDEM, what we're trying to do is solve this supply chain and national security problem by solving the environmental problem. How can we make the rare earths cleanly? Also, instead of utilizing mining resources that generate hazardous waste, we're actually taking hazardous waste from other industrial processes and cleaning it up to recover the rare earth elements. We have bacterial processes that we've genetically optimized that can leach and purify the rare earth elements to produce the pure rare earth materials that we need to make more magnets. Additionally, in addition to making sustainable rare earth elements from secondary sources, we also can convert the byproducts of this extraction process into what's called a supplementary cementitious material. These are materials that will replace ordinary Portland cement, which is a high greenhouse gas emission impact. We can replace that in concrete. So we are unlocking, billions of tons more of sources and feedstocks for rare earths and offsetting greenhouse gases to make a more sustainable built environment. So to give you an overview, we've got 2 key processes that we're developing in order to do this whole thing: bioleaching and bioseparations. My focus has been bioleaching. My co-founder's focus has been bioseparations. So I will admittedly talk more about the bioleaching. It's a bit ahead as well. But to give you the overall view of what we're trying to create, I'll start from the beginning, which is that we grow up our optimized bacteria that can convert glucose. The sugar, actually, we get it from agricultural residuals like corn stover and potato wastewater, which we have to break down with cellulosic enzymes. So there is some overlap with the plant science here. So we feed them glucose sources, and they then convert the glucose into what is called a biolixiviant. Another important word to think about, because I talk about it a lot. Basically, this is an acidic leaching solution. So we mix that biolixiviant with a solid rare earth feedstock that leaches the metals from the solids into the solution, which is called a leachate. The leached rare earth elements are then fed into our separation columns, where genetically optimized rare earth adsorbing microbes can purify and separate them. So we have different microbes that have different abilities to bind each of the metals, and so we're basically creating bacterial resin that act as chromatography to separate them from each other. All right, so at this point, this is an overview to why we're doing, what we're trying to build. I'm going to take you back a bit now to my postdoc and talk about how we got to the point where we wanted to commercialize it. So starting with the bioleaching, to dive a little more deeply, we're using Gluconobacter oxidans. So this is an acetic acid bacteria. It's gram-negative. It's non-pathogenic. GRAS is generally regarded as safe. It's acidophilic, so it works really, really well in that low pH of the biolixiviant. And then, most importantly, we can engineer it genetically, which was not the case for the arbuscular mycorrhizal fungi during my PhD. So this was an attractive option versus 4 months of an experiment. I could do something in 4 days. It's a nice transition into my postdoc. So basically, these bacteria, once they're at actual density, full density, they convert glucose rapidly. They incompletely oxidize it into gluconic acid. And this biolixiviant is actually mostly gluconic acid, but there are a lot of other elements as well that are clearly playing a role in the leaching of the metals from the solids. So then we take that biolixiviant, we mix it with the solids, and the gluconic acid generally leaches the metals from the solids into solution through acidity and also chelation of the rare earth elements. So like the gluconate ions are chelating the metals and leaching them from the solids. One of the first studies that was done with bioleaching with Gluconobacter, the rare earth elements, looked at a microbial solution, a microbial biolixiviant, and compared its ability to leach the rare earths from solids, compared that to abiotic gluconic acid concentrations. And interestingly, what they found was that even though the biolixiviant only has about 15 millimolar gluconic acid in it, a 90 millimolar gluconic acid was still not quite as well, as efficient at leaching the rare earths from the solids, which is telling us that it's really not all about gluconic acid. There are other factors that are playing a role here that the bacteria produce in that biolixiviant to get the rare earths out. And so what this told us was, let's go find out what they are. So my postdoctoral work was based on the genetics, was looking at the genetics of bioleaching. So to do this, I first had to create a whole genome knockout collection in Gluconobacter oxidans. So I said you can genetically engineer it, but truth be told, it is not like E. coli. It took some tinkering and maybe a lot of sweat, some tears, we could say. But I finally made that whole genome knockout collection in Gluki, as I love to call it. I then screened the collection of 524 96-well microplates to look for changes in acidification. So the easiest thing I could do was use a pH dye and apply it to the wells after adding glucose to see, okay, which strains had a differential ability to acidify the media. So for example, and what I did was I looked at the average of each plate, and then I said, okay, if you look at the average across the plate, where are the outliers? And that was how I quickly identified the different strains that had differential acidification. So for example, here, these two wells, this mutant actually had a lower pH than the rest of the plate, meaning whatever gene was knocked out in those strains, it was actually the same strain. I had some replication throughout the plates. Whatever was knocked out there, that gene was somehow repressing biolixiviant production. So I knocked it out and I got better production, right? Lower acidity. And then finally, I handpicked a bunch of the best hits and then tested them with actual rare earth bioleaching from a solid source. So overall, I was able to identify 165 genes that in some way seem to underlie rare earth bioleaching from Gluconobacter oxidans. As you can see, a majority of the hits were actually, you knocked them out and you had much lower efficiency of this is acidification, so less ability to produce acid, and a few that like really, really knocked out the acid production at all. But really interestingly, there were a handful that you knocked them out, like that previous plate I showed you, and the acid production got better. So I took the top performers from each end, and then isolated those in order to do the bioaging experiments. And most of those bioaging experiments were done sort of in flasks here. And as you can see, several of them had higher bioleaching efficiency. Extraction of rare earths was higher than wild type. And what's really interesting is that there was a trend. A bunch of these turned out to be part of the phosphate-specific transport system. So that led me to look further into this mechanism. So the phosphate-specific transport system is a system, it's a faux regulon, it's a system in bacteria that allows them to sense phosphate in the environment. It's a high affinity sensor, transport the phosphate, and basically in sufficient phosphate levels, the bacteria say, okay, we're good, we don't need more, and the actual faux B transcription regulator is repressed, and they don't turn on the phosphate starvation response. If there isn't enough phosphate in the environment, the repression is turned off, and the phosphate starvation response is turned on. When bacteria need more phosphate, they're going to secrete things that tend to break the phosphate up in the soil, release it from the metals that are chemically bonded to it. So it's no surprise that the bacteria are trying to get phosphate. We want metals, and it works together. So by getting rid of the repression system, we were able to upregulate the metal release. And among this transporter and sensing system, we had 5 hits in our knockout collection that had increased bioleaching capabilities, or actually acidification capabilities. A few of them had significant bioleaching capabilities too. So this was one key mechanism that we were able to identify. Then on the other side of the spectrum, we had a number with greatly reduced bioleaching capabilities. These 4 here, what we have as a MGDH, which is a membrane-bound glucose dehydrogenase. PQQC synthesizes the PQQ is a cofactor that the enzyme needs. And then these are also yet unknown to this system, but we suspect they're also involved in making the PQQ synthase cofactor, or PQQ cofactor. So just to give you a sense, MGDH sits in the inner membrane, and it converts glucose into the gluconic acid, and it relies on that PQQ cofactor in order to make this happen. So clearly knocking it out basically all but eliminated the gluconic acid production from glucose. So that brought us to our strategy. How can we take Gluconobacter oxidans and make it into a super bioleaching bug? And our first attempt was basically saying, okay, well, what if we both got rid of that repression from the PST system and increased the enzymatic activity of the membrane-bound glucose dehydrogenase gene? So that would increase the starvation response at the same time that it increases the conversion of glucose into gluconic acid. So this was towards the end of my postdoc. I did make this double mutant, and I explored a few ways to do it. First, we had to identify some high expression promoters in Gluconobacter oxidans. So we tried 3 here, TUF-B, and then these are just some numbers that we identified as high expressors, and we used them to overexpress the MGDH gene. We also knocked out not just PSTS, but PSTA, B, and C. The thing about the phosphate-specific transport system is if you knock it out, you can also get some growth defects, but somehow, and it's unclear still why, when we knock out PSTS specifically, the growth defects aren't that bad. It's sort of an extended lag period, but ultimately you actually get more growth once it gets past its lag period. So that was a positive thing for that mutant. And then we put it together, the PSTS, we overexpressed the MGDH gene in the delta PSTS background. So just looking at the pH of the biolixiviant, we had some effect of overexpressing the MGDH gene, and then the PSTS mutant had greatly lowered the pH, but then we saw this real additive effect with some of the promoters for overexpressing MGDH in that background. And when you look at the actual bioleaching of the rare earth elements, we saw a greater effect on the leaching itself rather than just the acidification. So it may not just be about acidification here. We could be talking about other factors that are increased in these mutants. So all 3 overexpression of the MGDH gene increased bioleaching. The PSTS deletion strain increased it more than that, but then putting them together did have an additive effect. Interestingly, P112, which has become our pet promoter now, to work with did the best, and it's neat to note that P112, I guess it did the best on pH here, but it really did well no, sorry, this is the thing. It didn't do very well in the pH. Sorry, the angle is off. Didn't do so well with the pH, but then somehow in the PSTS background, it did much better than the other promoters. So that makes us believe that perhaps the P112 promoter actually might be more active in the delta PSTS background. Okay, so this was basically the end of my postdoc. In fact, we're still working on revisions for this manuscript. And the identification of these double mutants and the amount that it had increased the efficiency of bioleaching really drove me to start thinking about, hey, how are we going to make this a commercial reality? Like we actually started with a system that had an economic analysis done. A group at Idaho National Lab, the same one that looked at the gluconic acid comparison, they did a techno-economic analysis, which basically tells you if you commercialize this, will you make money? And they said, yes, you will. It's not a lot, there's some margin of profit, but maybe not enough to get an industrial group to pick this up. So my co-founder and I thought, we've just increased this by about 70%. This is going to throw the economics in favor of actually commercializing it. So that's when we started putting together our thesis for taking it out and into the real world and making it, translating it into commercial application. But really, what's really cool is now at Regen, we've been able to start working with bioreactors and other types of materials as well. So this is actually coal ash. Coal, from when you burn it for energy, it concentrates the metals as it burns off the carbon, and those metals end up in the ash. And interestingly, rare earths do tend to occur around coal seams. So you see a lot of rare earths in coal in general, and then they get concentrated in the burn. So coal ash is a source of rare earths outside of mining. And what we were really excited to see was when we started working with some of the process optimization, we ended up realizing that processes, the process parameters were more of a bottleneck for this double mutant than we had imagined. And our effect of the mutation over wild type increased to 2 to 3x versus 70%. So that was huge. And if you notice, what we did was we started comparing regularly to concentrated, not 90 millimolar, concentrated gluconic acid and concentrated nitric acid. And we also threw in sodium gluconate, and we found that the biolixiviant from this double mutant was so powerful at extracting the rare earth elements, it almost matches the concentrated acids, which are just actually way too hazardous for any company to even use. So that was really, really exciting discovery and has led us down our whole commercial road. Also, to note, the sodium gluconate, which is not acidic, also leached a not insubstantial amount of the rare earth elements, which really lends itself to show that, yeah, there's chelation chemistry going on here that can get the rare earths out of the solids as well. Okay, so taking a step back, reminding you of the overall system. At this point, I've told you a lot about bioleaching. I do want to give you a brief intro to what's happening with the bioseparations. So this is predominantly the work of my co-founder, Jean Medine. He's also now Regen's Chief Technology Officer, CTO. He finished his PhD at the end of 2023, so he actually has only been at the company now since January of 2024, but he's really been taking off since he got there. So to give you a little bit more overview of how this works, you take a single column and load a solution of, say, 4 different rare earth elements. There's that NdPr, and then cerium and lanthanum, which we actually refer to as the weeds of the rare earth world, because generally cerium and lanthanum are more abundant in the Earth's crust than your NdPr, and they come out first, and you kind of have to get rid of them. They're only worth $2 a kilogram. They are used, but they're so abundant that they just actually contaminate the other rare earth elements. So the question is, how do we separate these? So if we have microbes that tend to bind NdPr over cerium and lanthanum, the solution that's mixed passes through, and your NdPr are going to bind. The free phase is depleted in NdPr, enriched in cerium and lanthanum, and flows through as a wash. And then we can elute the NdPr from the bacteria with a weak acid. We treat that, and we can rinse and repeat, basically. So this column is reusable over and over and over again. We actually haven't met its end yet. But basically, this is one column that would have engineered bacteria to bind certain metals over another, and with different columns with different specificities put together in series, we can get to a hyperpure, ultra-pure rare earth element. So the basis for these methods is the work that Sean did to do some mutagenesis. We're using Vibrio nitrogens to do this. It's a very large bacterium, incredibly fast-growing, genetically, tractable, really great microbe to work with, and it binds rare earth readily to its membrane. So he has been doing random mutagenesis in order to select for strains that bind higher levels of certain rare earth elements over others. And just as an example, if you look at this, this is sort of like how well it binds, neodymium over lanthanum, praseodymium over lanthanum. It's called a separation factor. There's a bit more math that goes into it, but just think of it like a ratio. He's been able to greatly improve how much is bound of the neodymium versus lanthanum. So this is the wild type separation factor, the ratio of neodymium to lanthanum, and he's pushed that up with this R3N3 strain. And I don't have it on this slide, but this is published, and you can find this in ACS Synthetic Bio. Sorry, I forgot that. Anyway, from there, the idea is that with multiple rounds of random mutagenesis, he's able to create a more and more specific strain. However, in his PhD, he was doing this with sort of random mutagenesis and selection off of plates in wells. And it's fast, it's throughput, high throughput, but not high throughput enough. So actually, now at Regen, he's building a microfluidic device. He has built it, and he's working on using it to select. So this is a template for that microfluidic device. And he's using it to select droplets with bacteria that have differential binding capabilities. So he's just increasing his throughput to like 10,000 strains in a day versus maybe 100 in a week. Almost there. I'm so excited. Every week I say, like, have we selected bacteria yet? But it's in development since he's come. OK, so that's going to help me transition a bit, because now he's at the company. And I just wanted to point out, so we founded in 2022. We actually founded in February, and we founded in order to apply for a grant that we were really, really not eligible for at all. But it also was great because founding the company allowed me to look into, OK, what is it going to take to commercialize this? And somebody told me about this Activate program, which is a national program first started out of California and Berkeley. The Lawrence Berkeley Lab had an incubator for startups to translate its research, and then they expanded into this Activate program, which has hubs around the country. They have Berkeley, New York, Boston. They just opened a Houston, and my first year in 2022, I was awarded the fellowship for the Anywhere cohort, which post-pandemic became feasible. We realized we can do things virtually, and so therefore we can reach entrepreneurs across the country that are not in these centralized hubs, which was really, really an amazing experience. I got the fellowship. We founded in February. I continued my postdoc. We started doing a little bit of commercial discovery. And then I got the fellowship and started working formally for the company full-time in September of 2022. This came with a $100,000 grant and salary for me for 2 years, which was amazing to be able to start a company with that sort of support right off the bat. This funding and support allowed us to get an exclusive license to the patents that we had created at Cornell. So Cornell owns the patents. We've now licensed them with decent terms. They have this fast track process that I think BTI, you guys are separate, you go through your translation office, but it is a process if you want to translate the research that you go through. They have paid tens of thousands of dollars to make this patent happen. You will get royalties, but you do have to license it for the company. It kind of made sense in retrospect. But with the funding, they allowed us to license it, and with the license, we were able to apply for and enter the Praxis Center for Vendor Development, which is a startup incubator here on Cornell's campus for engineering startups. Yeah, so that we entered in October. It took me forever to get a vendor agreement with VWR, but we finally got one and started working in the lab in January of 2023. And I say we, but it was really just me for a few months, and that was a really hard few months. I also bought a house and got married in those months as well, so I don't recommend doing them all at once. Thank you. But now we are 7 strong. So Sean and I, co-founders, CEO, we're the C-suite. And then we have 2 VPs. Brooke was actually in the Barstow lab with us, and after half a year, she moved to the company to help us run the lab. And then Simone is somebody from Ithaca who actually used to work at the World Bank, and she just really wanted a big change. So she joined us to help us develop our partnership interactions, which you'll see becomes very important with the company. And then we have 2 great lab scientists, and I just recently hired an amazing executive assistant, and she's making my life so much easier right now. We're also supported by tons of advisors and mentors. So these are just 4 key advisors. Of course, there's my postdoc advisor, Buzz, and then the director of the Praxis Center, who meets with us on a regular basis to help support, understanding what it takes to run a company. My Activate Fellowship was absolutely fundamental to my success for the past 2 years. And Hannah actually was with Activate my first year. She was my mentor. She has since gone off to start her own startup backed by Bill Gates. So she's actually done quite well with that. This is her 2nd startup now. And then also Marty Weems. This was a really key factor in getting the company going. He used to be the CEO of Western Rare Earths, which is one of the biggest upcoming rare earth mines that's opening up in the United States. Also, we have accumulated a bunch of support over the years. Over the 2 years, we started out with a great SBIR, so Small Business Innovation and Research grant from the NSF. We have a strong connection with the Air Force Research Lab. They have their Mid-Atlantic hub. And in fact, I would recommend even you guys look into this, because the Air Force Research Lab has a lot of directorates, and they're looking to collaborate with academic groups. And there is definitely some plant research going on there, or at least molecular research that could overlap with stuff that you are doing. And it's easy, it's I don't want to say easy money, but they're really eager to collaborate. And if you have a good idea, it's typically pretty straightforward and a low applicant pool to get your project funded. Fuse Hub is a local manufacturing grant that we were able to get, and the New Energy New York is out of Binghamton, and they've supported us with sort of micro grants as well. So in addition to Activate and Praxis, we're also part of an accelerator now, because technically my Activate Fellowship is ending this summer, and we've moved into the Venture for Climate Tech, which is a New York State accelerator for climate impact startups. And then we also have taken investments. At this point, they amount to about $500,000 investments. A lot of that became accessible through Activate, and I am currently fundraising more. So investors are a big part of my life right now. So to give you a sense of what we've done with that money and support so far, we sort of started out by looking at, remember, we don't want to mine. We want to be able to tap into all these secondary resources. And so we started looking at all these different possible sources for rare earth extraction, anything from magnet waste, electronics waste, can we recover those rare earths out of your phones and computers? And then there's the coal ash story. And then spent FCC is fluid catalytic cracking catalyst. This is used to convert petroleum, to make petroleum in refineries. These all have rare earths in them. But to look at all of these, we have spoken to over 200 different potential customer partners. We've gained 15 different stocks to test. And we've garnered support and so far acquired 7 letters of interest, which are actually a really great indicator that, hey, these people think that we will be able to commercialize, and they would be interested in our technology if we become successful, which we will. Through all of that, we have honed in on 2 particular sources. Coal ash, which is basically all over the United States, although we are phasing out coal-burning utilities. And then smelter slags, and this is an odd one, and we came upon it by accident, but basically if you look at the other metals that are being recycled, like steel, often what happens is the smaller metals, like the rare earth elements, can get concentrated when you purify the steel. They get concentrated into the slag. It's like that foam on top of the soup that you skim off is their slag, right? And especially with steel, because a lot of these steel products are recycled through magnetic separation. So if you're pulling the steel out with magnets, you're also going to pull out the rare earth magnets, right? So just looking at coal ash, they're 1.5 tons stockpiled in the US. That's a huge source, although we are phasing out. We still make 100 million tons per year, and some industries, it's going to take a long time for them to stop burning coal. However, the value of the rare earth in the coal ash isn't actually that great per ton, so that's a lot of input to get that amount out, but there's just so much of it, so this is definitely an area that we want to look into. There are also other monetary benefits to coal ash that we're exploring as well. However, for the slags from smelting other metals, we're still producing over 1 billion tons per year, and we can get up to $500 per ton of just the rare earth, and there are other metals in there to valorize as well. So we've decided to focus first on slag. On the left here, this is some steel slag that my summer intern went up to the Auburn Nucor facility and literally dug with a shovel out to take back to the region in order to test. He had permission, he had somebody with him. And then this is actually PGM, which is platinum group metals, and this is a really cool one. So automotive catalysts, your catalytic converters, everybody knows they get stolen. And they get stolen because they have platinum and palladium in them. So it's highly regulated, and the companies that recycle them, this is a huge industry globally, but they only recycle the precious metals. And what is true about your catalytic converters is that they have even higher levels of rare earth in them. So this became a significant source of rare earth metals to go after. Unfortunately, there are only about 50,000 tons of this slag that ends up being produced per year, but we've managed to talk to basically all of the producers, and this is our first customer. We're currently working with them to figure out exactly how the economics work. We have slag for most of them, looking at the processes and where the rare earths are coming out, and it's turning into a really, really great first project to maybe run into a pilot within the next 2 years. So to give you a sense of the data here, because I know we all love data, this is an example of the PGM slag. I just want to draw your attention to the different rare earth elements in here. So PGM slag, it has cerium, lanthanum, neodymium, praseodymium, and then some yttrium, gadolinium. And then the steel slag, what you notice is that the neodymium is actually the largest component of the steel slag. So there isn't quite as much of the rare earths in the steel slag as it is in the PGM slag. But the nice thing is you don't have as many of the other stuff to get rid of in order to get those magnet rare earth elements. And then if you look at leaching with concentrated nitric acid versus our biolixiviant, this is about 80% efficient. We've actually seen 100% as efficient and 100% extraction of the rare earths from these slags. There's something about the chemistry that this is a really great source to use our biolixiviant on, like the coal ash. And you'll also see that the PGM slag does generally have much higher rare earths than the steel slag, just less of it, and this is still significant. But to give you a sense of how much rare earth is in this PGM slag from the AutoCADs, here's a list of some of the rare earth mines around the world. And so Mountain Pass is actually the main mine in the US that produces, I think, about 30% of the rare earth concentrates. They all get shipped to China for refining and final processing. But you have mines throughout the world that are at different total rare earth concentration grades. So the PGM slag, 3% of that material is rare earths. So, okay, Mountain Pass, which is the top producing mine outside of China, is almost 9%. But this is a substantially high amount of rare earth elements. And if you look at just that magnet NdPr grade, we're at 1/10 of that is magnet rare earth elements, and that's substantial. Basically, this is a rare earth mine, but you don't have to dig it up. So big deal for us, and we want to go after that for sure. And to give you a sense of why neodymium is so important is that the demand for neodymium is really driving the rare earth market. So in general, the compound annual growth rate of the rare earth industry, the rare earth market, is 10.6%, but neodymium alone is expected to increase by 2.5 by 2050, and a lot of that is driven by electric vehicles. Is a huge expansion expected to drive the neodymium demand up. Unfortunately, the capacity for mining that we foresee having without opening new mines is substantially lower. So if we can really tap into some of these secondary sources, we can greatly offset the impacts of the additional mining that would be required to get that neodymium. So then we can talk about the impacts. We're not just impacting in one way, but if we put just like enabling those windmills, just as an example, a thought experiment, if we look at the steel slag that's produced from recycling steel in New York, Pennsylvania, and New Jersey, we can process on a yearly basis about 9,000 tons of that slag to get 350 tons of rare earths, that would be enough to enable 240 wind turbines. And so that alone, we're hoping to substantially impact the carbon dioxide offsets through the enabling of those technologies. In summary, Regen is seeing 3 key ways that we can really impact climate change positively, and we've estimated over half a gigaton, 500 million tons of CO2 offset per year. First of all, enabling this renewable energy that wouldn't be there because of the dearth in mining. Also, just the offset of that 65 CO2 ton equivalent for manufacturing the rare earths. And then also turning this slag, once we extract the metals, we're collaborating with a lab at Cornell to show that it can go into Portland cement, replace Portland cement to go into concrete, which is going to really offset the greenhouse gas impacts of that industry and also create materials for a sustainable built world. So, where have we been and where are we going? So in the lab, we were working in those flasks, right? And so with all the funding and support we received right out the bat, we've really been able to accelerate our progress. We've bought a couple of these 4-liter working capacity bioreactors in order to generate and really control the process parameters of biolixiviant and bacterial production. And that has allowed us to scale and start testing these different sources to extract about 1 gram of rare earths per week. That's not enough to be commercially applicable, so right now we're at the point where we prototyped bioleaching and separations. We have separations now in columns with bacteria, and what we need to do is scale that up and put it together. So we are building an integrated system where all of this can happen in tandem, continuously. And we've also looked to see about recycling materials, anything from the biolixiviant to the columns to the water that we use in the process. Everything needs to be circular. Currently raising $4 million, which is my full-time job right now when I'm not talking to you guys, is talking to investors, because we're looking to get that $4 million by the end of the year. We're moving into a new space. We're going to make more hires and start scaling the equipment. So in 2 years, our goal is to have this scaled integrated pilot with one of our potential partners, likely in the AutoCat recycling world, to say, hey, we can take your 50,000 tons per year and convert it. And that pilot demonstration is going to lend itself to our next raise, which will support commercial application and actually bringing in revenue from converting all the slag. So our goal is by 2028 to be ready to enter the market, have a sales agreement for the extracted metals, and actually be generating substantial revenue. At the same time, we'll be building a facility here in New York in order to take the rare earth concentrates we get from all those slags to process, refine them, and separate them to sell the rare earth oxides to downstream buyers that will eventually make magnets for the wind turbines. So that's where we're at. And just as a shout out, this is where the magic happens. We're currently on the engineering quad on Cornell's campus. This is in Kimball Hall. This is our little lab space that we stuff all of those scientists into. Good thing we like each other, but we are tight. And we are hiring, so please check out our LinkedIn for the job postings. Any of you would be great candidates. You don't have to have worked with metals. We need molecular biologists. That's a really big one. So if you have great skills at cloning and engineering microbes, and even eukaryotes, because we'll be doing some fungal work as well, please do consider this as an option. And we do have a really great team, and we have a bunch of equipment now that we can't wait to be able to use in January when we're in our larger space. So with that, thank you for your attention.
Questions?
Sure.
So I was kind of curious, once you've reached up and eluded it off the column, how are you figuring out what you have and how pure it is?
Yeah, that's a great question. I mean, generally right now we're using ICP, mass spec, so ion coupled plasma. I don't say these acronyms very often. So ICP-MS. We have access to a machine. Actually, it's racking up many, many bills for us, but luckily we get internal rates in the geology building. So, yeah. Yeah. Thank you.
I was
Biolixiviant, yes.
What are you doing? Like, how harmful is that to the environment? And do you have any plans on like kind of turning it back into a high pH with those microbes?
Yeah, that's a really good question. So this is live streamed. I'm not going to give away any. It's fine. Don't. But so I would love to share that actually the pH does come up when we mix it with the solids. So we don't actually have any sort of hazardous material when the process is done, except for the heavy metals, which we extract. And once we extract the heavy metals, we're actually reusing the biolixiviant to continue leaching. So we have a way of regenerating it and reusing it to leach on a continuous cycle. Ultimately, at some point, that will be spent. And one of the things, as a plant scientist, I would really love to explore is, could we even like use it as a fertilizer? You know, because it is nutrient rich. So, yeah. Oh, sorry. Go ahead and then. I should also repeat your questions. I meant to do that.
Okay. While you're in this testing phase and you're not commercialized yet, or you're not receiving all the waste from the industry, where are you getting your testing waste, I guess?
The testing material that we use? I mean, we have strong connections with industries. So in fact, I had a conversation 3 weeks ago, and he's like, if I sent you 10 tons of slag, could you take it? And I paused, and I like imagined how big my property is in Fall Creek, and I was like, I literally asked him, I was like, what are the dimensions of that? And he told me, and I said, yes. But they're not going to do it yet. I said, let's wait until January when we have a larger space to process it. But yeah, no, we have really strong connections with all these industries that are sending us samples. They're really excited to see what we can do with it. Of course, the economics have to work out. Money's the bottom line for them. If we can't save them money or make them more money, they're not going to do it. But they are incredibly inspired by the vision in order to, you know, take a risk with us and pay for some shipping of materials. Yeah, thank you.
Hey.
Hey.
Are you close to being able to produce the number of kilograms of rare earth metals to make your company financially sustainable?
So we are about 2 years away from that. So it's a difficult, because that's a very subjective answer. Right now, our capacity is processing about 1 kilogram of material at a time, which only gets us about 1 gram of the NdPr from those slags. But there's literally the main thing that's getting in our way of scaling that up is space to install the equipment and lead times on the equipment as well, but we're working on that. So close is, we have no reason to believe that this should not scale. So far, it has only improved with scale at this point. The bacteria are hardy. This is not your typical fermentation of proteins that looks at a lot of scaling issues. So fingers crossed, we believe we are. And as soon as we have more space and more equipment, we should be able to quickly scale. Thank you.
I just wanted to ask, how did you decide that forming your own company was the best next step for this idea that you started in your postdoc, and how was that transition to industry?
So 2 very good questions. So how did I decide this was the best next step, and how was that transition to industry? I did not decide this was the next best step. I just saw it and I leapt into it. But I have not had, sorry Maria, more fun doing what I do since like ever, basically. Yeah, I mean it's also the worst job in the world sometimes. Like I was literally in tears worrying about getting some money because I've got all these employees that I have to support, and I'm sure that many of the faculty in this room can relate to that as well. But it is just so inspiring and exciting to be working with industries that are doing things to make money, like just solving people's problems, basically, is what we're doing. It's not for everyone. I mean, I also really love basic science and exploring, you know, what makes things happen the way they do. And actually, my co-founder and I, that's one of the biggest things we have to check with each other is like, do we really need to do that experiment? Is that really going to push the needle at all on the business? Like, I agree, it's super cool and interesting, but only if you really have nothing else to do, you know? So it's been a process. I also absolutely love teaching and mentoring. So I thought I was going to be a faculty hopefully at some point. But this happened, and honestly, I feel like I'm a PI with a lab. So it's been an amazing experience. I think what I would say is just see this as one of the possible avenues you could take. And it doesn't have to be your work. So you could even like go to meetup groups or classes on entrepreneurship and meet other people interested in starting companies and start looking into ideas together. And that can also be how you start a company. You might have the expertise and you find an invention somewhere that you're like, that'd be cool to commercialize. It doesn't have to be yours. So just something to explore as an alternative to the other avenues that you're looking at. I think we have one with the mic here.
Hello, is this on? Great talk. I was wondering, so you said the bacteria are binding to the NDPR and the CELA is released in the solution, right? Mm-hmm. What's the like proportion of each of those that you usually get, and is one of those more valuable than the other industrially?
Yeah, the proportion, they bind both fairly well. The proportion is more like 1.5 to 1, 2 to 1, but because it's chromatography, it's about also the separation length and time. So all of those factors contribute to how well they separate from each other. NDPR is currently around $40 a kilogram, cerium lanthanum $2 a kilogram. NDPR, that's quite low in value. It's so this is the issue with having one country monopolize the supply, is that it's gone from like hundreds of dollars per kilogram to 40. It's at a really low point, and then it's probably expected to rebound. We're looking between like $75 to $100 per kilogram for neodymium or praseodymium. So substantially more economical to recover the NDPR. Though we would still want to sell the cerium lanthanum if we can. We don't want to throw it away. So.
Thank you.
Yeah, thanks. Thank you.
When I think of basic science, sometimes there's some great findings that don't really lead to an application or process that is commercially viable. And I think you had an amazing story of how like the cost analysis actually made this a potentially applicable idea. And my question to you is, how do you get to that? Do you get any assistance from like an economic analysis to help you decide whether this was a good idea to pursue?
Absolutely. I do want to make one comment on the basic science, because all that phosphate-specific transport, I mean, you see how basic science has really lended itself to us understanding how we can make this commercially applicable. In terms of figuring out if we would make money with it, yeah, so there are researchers and consultants, and so we consult with a Cornell alum, actually, Burke Techno-Economics, Chris Burke. He's a fantastic person, and he helps us develop our techno-economic analysis. But there are also research labs that are specialized in this. So often what you'll see is a science lab will collaborate with a TEA lab, and they'll put their efforts together to show like, okay, we've got a technology, can you help us figure out if it could be economical? And that was the basis that came out of the Idaho National Lab that drove us to want to actually commercialize it. Yeah. Back here?
Do you think that gluconic acid is the best biological chelator? Have you had others? What is the scope of testing?
Yeah, so the question was if gluconic acid is the best biological chelator, I guess in this solution or maybe overall. And what is our scope? Have we tried others, and what is the scope of testing that? So there is some literature looking at different organic acids and how well they can extract rare earth elements, specifically from coal ash, actually. Citrate works well, but gluconate has performed better than all of the others, which is really more about, like, that was not the basis for using gluconobacter, but it just sort of validates that we continue using gluconobacter instead of looking at bacteria or fungi that are producing some of these other organic acids. So this came out of a study that looked at a variety of microbes, and this microbe performed the best. It's likely because it has high levels of gluconate, and then also the metabolic derivatives. So like 5-ketogluconate, 2,5-diketogluconate, they are also really great chelators, and we haven't been able to test them yet because time, but we will test them. And we're also looking at all the different constituents of the biolixivian to see what else might play a really key chelation role. Yeah.
It seems like you have a process, you have the rare earth sources, Would you say that a major part of what remains is literally an engineering aspect, bigger pumps, bigger columns, leaching tanks, and et cetera?
100%. So we're at the point now where we're ready to scale. We need space, we need engineers, we need consultants. I'm actually looking to get a strong EHS consultant. Like, we're in that position now where we have to think, like, what is this manufacturing process going to look like? What sort of permits do we need? What sort of safety considerations do we need? And for that we need money, which is why I'm raising $4 million. And then that will be the first process. And then once we've really shown, okay, larger scale this works, I'll be raising the next chunk to say, okay, we're going to commercialize it. Yeah. Thank you.
Your process for Portland cement.
Yeah.
Because I know that coal fly ash is like a viable replacement in Portland cement, and I'm curious how that ties in with your extraction of rare earth elements, or if that like gets messed up in that process.
Yeah, great question. So what is the prospect for using this coal ash as a replacement for ordinary Portland cement? I'm really glad you asked that, because I didn't really have a chance to put it in. It just felt like it was more, I didn't want to overwhelm you guys. But so basically, coal ash and steel slag are both actively used as replacements for ordinary Portland cement, which requires a lot of heat and even coal burning in order to make. And then the coal ash for energy utilization. And the slags from recycling steel can basically say we don't have to make the ordinary Portland cement. We can just take these byproducts and put them right into the concrete industry. In fact, they can confer better strength for concrete than OPC, ordinary Portland cement. So this is a huge industry in itself. And when we first started looking into using coal ash, especially fly ash, certain classes of fly ash, and the slags, our biggest concern was we did not want to disrupt that value chain. We can't come in and take all the fly ash. That is actually a really big industry for the concrete industry. And so that's when we started thinking, like, what if we could extract our metals and then process it in order to still like stay in that value stream and go into cement? And it's looking really promising for that. And that is why we have the collaboration. And I'm waiting. I told Delaney I wouldn't check my email, because any moment now I will get my award notification if I got it or not for a $1.5 million grant to actually pursue that. So fingers crossed. Yeah. His mic.
I was wondering, because how is your process comparing in terms of like water use efficiency, especially because bacteria, they need to have some kind of media. I don't know how that works with more traditional processes.
Yeah, so the water use is a great question. So what does our water use look like, and how does it compare to like conventional methods? The water use is less, so conventional mining and separations does use exorbitant amounts of water. But at this point, I mean, we do need to explore ways to remediate the water that we're using. Luckily, it's not hazardous waste, so we don't even want to throw it away. We really want to employ, and there are lots of technologies that we can use to clean it up. We haven't started exploring that yet. That'll be part of the next phase, is saying how can we keep the water circular. In terms of growth of the bacteria, so yes, that uses a lot of water, but what we are finding is that we can grow the bacteria continuously and basically pull the biolixiviant out without, like, we separate it from the bacteria and continue to add glucose. And that process, once they're grown, and then we can run that for, we don't know how long yet, but we've already like done it like 10 times in batch, and we're trying to set up the continuous system to see how many days we can grow it, which is a huge part of the economic model. The less we have to regrow the bacteria, the less operational cost we have of creating the biolixiviant. But ultimately, yeah, we want to keep our water circular inside of the company. There's not a high purity demand for anything that we're doing. Well, the separations will need high purity, but in terms of the growth and the extractions, it's okay. Yeah. Sure. Yeah, how much time do we have? One more? Okay.
Speaking of environmental concerns, I'm wondering, going from a transition from a fundamental basic scientist to now it seems like an entrepreneur, and to go into a very business perspective, sure. Have you run into any ethical concerns, and how have you tackled them?
Yeah, this is a great question in terms of ethical concerns. I wonder, well, let me just address the things that come to my mind. A big concern that we have is the genetically modified microbes, right? So this, I'm sure that everyone here is very familiar with the issues around GMOs. When I was at BTI and a plant science researcher, I was very, very passionate about education around genetically modified organisms. So we've actually spoken to several regulators in different states, including the EPA, federally, to ask exactly that question, like to what extent are the GMOs in our process going to be an issue? And oddly, they just don't even know. They're like, I don't think it will be, we're not sure. And so we don't take that as like a free rein to do what we want. We're taking that as, you know, keep it in mind and talk up front and try to get it regulated early so that we're not running into an issue where we're ready to run a project and they're like, hold on, you've got GMOs, we can't let this project happen, we need to regulate, we'll come up with, you know, like how we're going to, you know, handle it. We need to put out regulations around what you're trying to do because it's so new. So that's kind of like the biggest issue that we've seen. However, we are not actually releasing the genetically modified bacteria. So they don't touch the solids. So overall, the genetically modified organisms never leave the process. So there is a potential, you know, to kill them and release like you would do in a lab here. The other ethical concern is just what we do with the waste after we're done with it. If we can't make a supplementary cementitious material, we probably will have to either landfill or sell it into other applications like road blast or sandblasting. And our aim is to test our byproducts, the solids, if they will not go into building material. Well, either way, no matter what we do with them, our goal is to keep the heavy metals and the contaminants in those solids below the thresholds and never have them go into the water. Like that is part of our vision. The impacts are huge. They come first. So, yeah. Anything else in particular that came to mind?
Oh gosh, no, that's an excellent answer. No, I'm very glad to hear that.
Yeah, thank you.